bunch of assets together, all those, the firm-specific risk of the resulting portfolio, if the portfolio is large enough, will be eliminated. Then we use this also to figure out the covariances between two assets. So, given that the firm-specific shocks of company I and company J being two different companies, the firm-specific shocks should be unrelated, right? If they are totally independent. So given that this is like that, then by doing some mathematics that we didn't do and you have no prior knowledge of, you can figure out that the covariance between the returns of I and the returns of J is equal to the bet of I, the bet of J, sigma m squared. So this is how you can calculate the covariances between them. So this is the essence of what we did last time. There is a little bit more, and we said that in a portfolio setting, the beta of a portfolio is the weighted average of the betas. So we applied that, and then what else did we get? We also said, since sigma p, the risk of an asset, can be written as weight of x, risk of x, so let's put this as squared. Weight of y, risk of y, squared plus twice weight of x, weight of y covariance, xy. And sigma p can also be, according to this model, can be written like that, can be written as beta p, sigma m squared plus sigma EP squared. And then you can use those two equations combined together to figure out the diversifiable risk that is contained in a portfolio. You can combine the two equations to find the diversifiable risk. So you can find this guy. Okay? So those were all the applications that we did last time. Questions? Sorry, this is all fun and all, but this is just a theoretical model. So we made a bunch of assumptions. Can we actually estimate this in real life? So how can we estimate the model? Using real data. And so if I want to estimate this model with real data, I need to identify a market-wide factor, and I need to identify the sensitivity. I need to measure the sensitivity of that asset to that market-wide factor. So typically, we use excess returns. What are excess returns again?
It's your return you got minus the expected return.
No,
Minus the risk-free.
it's minus the
Risk-free,
history rate.
whoopsies.
2 strikes, that's it. So you use excess returns, which are defined as, that was the big R, I comma t is equal to the little return of I, time t minus the risk-free rate. Okay, so it's what you get in excess of, think of it as the lowest return that is to be expectable. So I use excess return to figure out the return of I, and then you pick a large portfolio as a proxy for the market. So what can you think of a large portfolio that is easily, that you can find easy, that could act as a proxy for the market?
S&P.
Just pick an index, right? And that gives you the same type of behavior of a large portfolio. So the most likely that you can find is the S&P 500. So this proxy for the market, this portfolio is called the actual index. So those are called factor models. This is called, it's going to be called an index model, and compute its excess return. So you have the big R of the market, comma t is equal to a little r of the market, comma t minus the risk-free rate. Okay? So in trying to estimate the model, in trying to figure out what the beta is, we're going to use regression. And your model is going to look like this. You have the big R's, the actual returns of, the actual excess returns of I as a function of a constant that is unique of I, plus the beta of I, the excess return of the market at time t, plus the other term. So those are all observed values. We collect data about the returns of the stock, the returns of the market. So picture it, a data set that looks like these. These are the returns of I, sorry, excess returns of I. Excess returns of the market over time. You match them up. So every day you try to fit this thing, and then somehow you average it out. So ultimately, when you do regression, you estimate this value, and you estimate this value. Now, if you do an average of all those subset equations that you can create in here, on average, you will have that the average return of I is equal to that alpha plus the beta of I, the average return of the market. And what is the average of their returns?
0.
This is actually true when you're dealing with regression, right? Regression is, you're finding the slope so that the average of their returns by construction is 0. So by doing this, we actually have estimated the beta, the sensitivity of asset I to the market-wide shock. Yeah. What about the alpha?
Should be the risk.
So, well, the risk-free has been taken out in this operation. So, if the only component of returns, the only component of market behavior that gives you, that is responsible for return, given that those are 0 now, on average, it should be just coming from these. So, this is a market, a premium due to the market. or to the common factor. But this alpha, if alpha is positive, is a non-market premium. So if this alpha is positive, that means that the returns of this asset, on average, are in excess of what you should be compensated, given this asset's sensitivity to the market. Yeah, what about if alpha is negative? That means that the stock is producing, on average, lower returns, given its beta. Okay, so picture doing this for a bunch of different stocks, and this would allow you to find the stocks that, given using this historical data, have overperformed if alpha is positive, or underperformed if alpha is negative. Does it make sense? And assuming that this behavior is projected to continue in the future, then you can create a portfolio of assets with a positive alpha. Assuming that those assets will continue to have their positive alpha, now you've identified a winning portfolio. Now, what do we know about past data's ability to predict future data?
It's not 100%.
It's pretty low, right? And so, be aware of that. In theory, it would work. In practice, well, if a lot of people are using this technique, even if it worked, eventually this technique is no longer going to work anymore. It's already embedded in asset prices. Questions? So this is something that you could possibly do, right? You have your ETFs, and the way you have collected data, let's suppose you take excess return, you calculate the excess returns for stock one, say Apple, and you do the same thing for GE and so forth. So you collect several data sets. Then you calculate the excess returns for, say, the Spider, which is an ETF that follows the S&P 500, and now you can estimate the alpha and the beta for Apple using those two. Then you can estimate the alpha and the beta for GE and so forth. The way you do it in Excel, there is a regression tool. You have used that in EcoStats. That's pretty much the way it works. Questions? So if you remember about the different studies about market efficiency, the way you calculate abnormal returns, the abnormal return is the actual return of the stock minus what is predicted by the model. So if you think about that, suppose I estimated alpha and the beta for the particular stock. I see what the market does today. By using this, I see what the stock should have done based on this model. So I compute this value by using those two and what the market does. But those three numbers, all those numbers are basically this guy, this guy, and this guy. So the actual behavior of the stock differs from the predicted one by this parameter here. So all you need to do is calculate the model, collect the residuals from the regression, and you can think of the residuals as the abnormal returns of the stock for the particular day. If you want to see what many stocks do around a specific event, then you collect the residual of each stock in conjunction with that particular event taking place, and then you do this average, you average out all those abnormal returns on those days to see if they're positive or negative. If you find statistical significance, that means that the particular event either makes the model not work, or the particular event is associated with a specific movement of the stock, which is associated with abnormal behavior. Now, there is a non-market premium around that particular event. But you don't know which one is which. You don't know if it's the model not working or there is actually an abnormal behavior of stocks in conjunction with that. If you remember, this ambiguity, we give it a name, right? We call that the joint hypothesis problem, where you're testing two things simultaneously. One is a model that you don't know if it really works, and the other one is an event that could possibly alter behavior. Questions? So there are variants of this thing where you look at the returns of your portfolio against the returns of the benchmark. You run a regression basically like that, and you collect this alpha. So in that case, you're trying to figure out your performance relative to the performance of your benchmark. You're scaling down for possible differences in risk. So if the risk is the same, then this beta would be 1. If the risk is different, then this beta is going to be either lower or higher. Higher if your portfolio is more risky, less than 1 if your portfolio is less risky. And then you look at the alpha. If the alpha is positive, it means that even after you take into account differences in risk between your portfolio and the benchmark, you were able to produce abnormally positive returns. Conversely, if this guy is negative, then after taking into account for risk, your portfolio has underperformed. Okay. So we're going to see that measure of risk, that assessment of performance towards the end of the semester. But essentially, it's an application of that using specific data set. Questions? Alright, so now we know all that stuff. Let's move on to multi-index model. Now, one thing to keep in mind, if you remember, this whole model was developed so that we could estimate covariances just by running a regression and obtaining the beta for each individual asset. And then if you want to estimate covariances, all you need to do is multiply the betas, which is much more computationally more efficient than matching each individual stock with every other one and calculate all the possible covariances. One of the issues with that, the more calculations you make, keep in mind that this data is not exact. There is some errors, there are some anomalies, and you might end up with, when you try to calculate all the possible covariances, you might end up with a covariance matrix that is inconsistent. For covariance, let's use the correlation matrix because it makes more sense. So let's see, this is an example of an inconsistent correlation matrix. The correlation between something and itself is always going to be 1. So those are it. Now let's suppose A and B always behave the same. Then the correlation between them is 1. Do you agree with that? And the correlation between A and C is also 1. Measure it. What should be this one?
Should be 1 as well.
Should also be 1. If this guy, if A always does, A and B always do the exact same thing, and A and C also do the exact same thing, it follows that B and C should also do the exact same thing, right? So an inconsistent matrix is when you have this scenario and this number is not 1. And keep in mind, when you're using data, there is a margin of error around each measurement that you make. And so you might end up in a scenario where the real values are 1, but the measured one is 0.8, 0.85. This is 0.93, and this one could be 0.2 just out of measurement error. So that you have a large measurement error there. So when you try to use this matrix to do all the calculations, the mathematics just doesn't work. It just fails. It fails completely, or it's gonna give you some answers that are totally messed up. One of the things that you might want to experiment with, you have your next project, right? Trace the frontier. And then just out of curiosity, artificially change one of the correlations and calculate the ideal weights that minimize the risk for a given level of standard deviations. And you see that the portfolio is gonna be totally different just by changing the correlations by a tiny bit. So the whole Markowitz process, the one that we learned about finding the ORP, is highly dependent on this correlation matrix or covariance matrix, okay? And the more data you have, the more likely you are that you encounter this scenario. So this thing is reducing the likelihood of that happening, but you're making some very strong assumptions, and the assumptions are about the distributions of the returns and all these error terms and everything else. And if you go back to, I believe it was chapter 5, when we looked at the behavior of returns, the empirical behavior returns, we know that returns are correlated to some degree. Sometimes the standard deviations grow and they stay wider for some time, then they shrink a little bit and they stay smaller for some time. So there is all this kind of behavioral returns that could make you question whether those assumptions hold, and therefore whether this method is applicable. Questions? Now, one thing to keep in mind, the structure of this thing, the way this kind of looks like, is kind of similar to the capital asset pricing model, right? Is the equation, the capital asset pricing model essentially is the equation of a line. But it turns out that to estimate and test CAPM, they use pretty much the same equation. And in that case, in the setting, this will be the CAPM beta, which mathematically will be computed the exact same way as these when you're doing those tests. But under CAPM, we arrived to the capital asset pricing model by using a completely different approach. We are using this technique, but the logic to find the CAPM beta is different than that. And those are just statistical assumptions to simplify the estimation of the matrices, the covariance and correlation matrices. This is a practical application of it. And CAPM just lives a completely different life, which ultimately leads to a mathematical model that kind of resembles this. We're not going to talk about CAPM today, we're going to do it next time. We're going to look at the theory behind it. The natural extension of this thing from a single factor model is to extend it to multiple factors. So multi-factor model. So the idea of the multi-factor model basically is the same as what we did here, where we say that the returns of an asset can be modeled as a constant. Plus, let me make sure I use the notation from here. Yeah. B1 of I1 T. B2 I2 T. B AI I k at time t plus E of I at time t. So let's see what this means. I1, I2, I3 is the value of a risk factor. So we need to give it a name, but since this model doesn't tell you what those risk factors are, we just call it by its number. We call it risk factor number 1 at time t. I2t is the value of risk factor number 2 at time t, and so forth. Risk factor number k at time t. Okay. What about the associated values of B? B1 I is the assets I. Sensitivity to risk factor number 1. And beta 2 I is asset I, sensitivity to risk factor number 2, and so forth. So there are different sources of risk. An asset has its own sensitivity to each of them, okay? What about this EIT? Well, it's still the firm-specific shock, right? So the error term. It's firm-specific shock at time t. And this alpha I, or AI, is the equivalent of this expected return of the stock. Okay. And the big RI, the ARM IT, those are the actual return. Asset I. Okay. So picture this model, but now we have multiple sources of risk. In this particular case, this could be the equivalent of one of those I's. This could be only I1, there is only one of them. And this would be the sensitivity of the asset to that particular risk factor. So, what are the assumptions here? Well, the first one is that the error terms must have its zero average and some spread. The other one is that each risk factor is unrelated to the others. So each of them only captures one specific aspect of risk that cannot be captured by any of the other ones. So this means that the covariance between risk factor I and risk factor J is 0 if I and J are different. So that if you're looking at two different risk factors. What about the covariance between the risk factor and the error terms? How should that be?
0.
Well, those are firm specific. Those only measure one particular aspect of risk, not captured by anything else. So they should also be 0. One way to describe this using words is by saying that all those terms are orthogonal, which I don't know how to spell. I think it's like that, with one another. What does it mean that they're orthogonal? Two lines are, if two lines are perpendicular to each other, we say that they're orthogonal. Is that right, in geometry? So what this thing is saying basically is, if something moves up and down here, I can capture its location only by using this coordinate. There is no way to capture this movement by using the coordinates on the x-axis. So one coordinate only describes one type of movement. Something that moves left and right here can only be captured by changing values on the x-coordinate. You agree with that? So what they're saying there is that something that is moving in one direction only affects one measurement, one I, and does not affect the others. And orthogonality basically means that all those variables are uncorrelated with each other. Yeah. So that's pretty much what they're trying to establish here. What else? Okay, so just to follow pretty much that general logic, then what is the risk? On average, the average return of I should be equal to AI plus beta 1 of I1 average plus B2 of I, the average value of I2, B, the last one is K, BK of I, IK average. So the average behavior in asset is to follow these. What is missing from that list?
The error term.
The error term, right? Why is it not there? Well, because what is the average of the E? The average is 0. So the average up to that. Alright. So the next thing that we did in here, we said, well, given this model, we established the covariances between all the different assets and their statistical properties. Let's figure out what is the total risk. So this is the first conclusion. Second conclusion, the total risk sigma of asset I squared is equal to beta 1 of I sigma 1 squared plus beta 2 of I sigma 2 squared beta k of I sigma k squared plus sigma e of I. So where are these sigmas over here? This is the variance, I'm sorry, standard deviation as I wrote it, of risk factor number 1, standard deviation of risk factor number 2, standard deviation of risk factor number 3, and so forth. So what is happening here is that now systematic risk is decomposed as coming from multiple sources. And this guy right here is the same term like that, is the firm-specific risk. Okay, so this expansion of the model is permitting us to get a better picture of what this firm-specific risk is. It can come from different angles. Questions? So we dealt with this, we decompose risk again, systematic and firm specific, but now we have a more clear picture of what systematic risk might look like. And then the last one is, let's figure out covariances. What is the covariance between the returns of asset I and the returns of asset J? Well, somehow you have to multiply the sensitivities just like you did there. So it turns out that the covariance between those two guys is beta 1 of I, beta 1 of J, sigma 1 squared. Then beta 2 of I, beta 2 of J, sigma 2 squared, all the way to beta k of I, beta k of J, sigma k squared. And what about those guys? What is the covariance between the firm-specific shocks of a firm with the firm-specific shock of another? They should be unrelated, so they should not take part of that. Questions? So the last thing is, what if you mix assets in a portfolio? For a portfolio, beta each sensitivity of the portfolio is obtained by the weighted average of the corresponding betas. B's. So for example, beta 1 of the portfolio is equal to the weight of asset I, beta 1 of I, plus the weight of J, beta 1 of J, plus we do that for all the assets of the portfolio. The beta 2 of the portfolio is the weight of asset I, beta 2 of I, weight of J, beta 2 of J. And you continue like that for each of the assets in the portfolio. So you repeat this calculation for each of the risk factors. Questions? Is it disgusting so far? Yeah? It should be. It's meant to be that way. So let's try to summarize things and let's try to see if we can make it simple. So what is the story here? We're saying, well, let's suppose, what if there are more sources of risk? How can we handle it? Well, clearly you cannot just ignore one of them, because if there is several of them, you should include all. And in fact, if you exclude one, then your models are going to be not measuring risk correctly, and they become a waste of time. So the assumption here is that there are different sources of risk, and each asset has its own unique sensitivity to any of them, to all of them. Now, how should these risk factors be measured? Well, they should be such that each source of risk cannot be explained by any other source of risk. So they're completely independent of one another. Like for instance, let's suppose that I think that one of the sources of risk could be oil prices. Should another one be gas prices? Probably not, because if oil prices go up, most likely gas prices also move in the same direction, right? So I don't need two sources of risk. I can just use one of the two, and it would work well enough. But what about interest rates and price of wheat? They don't appear to have an immediate connection, so they should not be highly correlated with one another. Now, would they make sense? Well, maybe for banking, the level of interest rates would have an impact on the returns of banks, but definitely the cost of wheat is not likely to have an impact on it, right? So there are two things that measure two different things, and one company might have significant exposure to one of the risk factors, but almost no exposure to the other. But nonetheless, those two risk factors could coexist. Now, for a company that is highly leveraged, perhaps, that makes bread or food products, then maybe both betas would actually be different than zero. That would have an impact on the performance of that firm. That's pretty much what this model is trying to say. Use different sources of risk. The sources of risk should be totally unrelated with one another, because if they are related, you're better off using a single index model. And if you meet those conditions, then you can decompose risk this way by looking at the sensitivity of each of the particular stock to each of the individual risk factors. And then there is a component of risk that is unique to the firm. That's pretty much what the story is telling you here. Now, if you want to get more sophisticated, you want to see how two companies are related, are interrelated, but their degree of covariance is linked to their similarities in terms of betas, for the betas of the same risk factor, the volatility of their risk factor, and all of them work towards adding covariances or correlations between the returns of those assets. If you're dealing with a portfolio, then all you need to do to find the set of betas for the portfolio, each beta would just be the weighted average of the betas of the assets you're mixing in it. So let's see if we can make sense of this thing. Let's do an application. All right. So consider the following two-index model. So two-index model, what am I saying? What does it mean? Two-index models means that there are only two sources of risk, right? So for every asset, I will have to give you each of the betas, right? Every asset will be described by two betas. So you have asset X, Y, B1, B2, 0. 0.5 and 0.7. Okay. And then, so then you have the average value of the index. Three and 5. And then let's suppose that H0 is 0 for all of them. And then sigma I, standard deviations of each of those guys are 10% and 20%. So this is all the information that we have. And so let's try to figure out part A. What is the average return of X? Part B, what is the total risk of X if sigma EX is 1%. C, what is the covariance between X and Y? And then D, what are the betas for a portfolio invested 40% in X. Okay. So what is the average return of X? We're going to look at that particular formula right there for part A. R bar of X is equal to A of X plus B1 of X I1 plus B2 of X I2. You agree with that? So those are the only risk factors that we have, 1 and 2, and on average they have returns at 0, so we're using this thing right here. So the average, the expected return of X is zero. B1 of X is 1. The average level, so I forgot to put a bar on top. The average level of I is 3. B2 is 0 for X. And I2 is 5. 50%. Yep. So pretty straightforward, just tedious. What about part B? We are looking for the total risk of X, so sigma X squared. And how to compute the total risk is decomposed into different parts of systematic risk, and then there is the firm specific. So you have beta 1 of X, sigma 1, both squared. Beta 2 of X, sigma 2, both squared, plus sigma E X squared. There's only two sources of risk. So now put the numbers in here. So when you're doing those calculations, you have to use it in decimal form. If you don't want to mess with percentage squared, it's up to you. The choice is yours. So beta 1 of x is 1. Sigma 1 is 10% squared. Then you have beta 2 of x, which is 0, times sigma 2. Sigma 2 is 20%. And then you have 1% sigma ex, right? So 0.01 squared. So the calculations are carrying over are the exact same for the single index model, but a bit more complicated. So this is 0.01, is that right?
Yes.
I don't know how many zeros I have to carry over. So this is what? E minus 2 squared. 1, 2, 3, fourth place. Should be right. Do you ever use scientific notation? Yes, no?
Mm-hmm.
Anyhow, use the calculator, tell me what you get. Zero point 0.0101. Is that correct?
Mm-hmm.
So what is sigma x?
$10.1%.
10.1%. Are you sure? No, take a square root. You did?
Yeah.
10.1.
Yeah, it's kind of weird actually. Well,
Are you sure?
yeah, I just rounded up. Technically it's 0.1004. I just
Okay.
rounded.
So 10.04, right? Percent.
0405, yeah.
Okay. Questions? So we got took care of this guy, took care of this guy. Let's look at covariance. What is the covariance between x and y? It's b1 of x, b1 of y, sigma 1 squared. Yeah? Plus b2 of x, b2 of y, sigma 2 squared. That's it. It's only two risk factors. So with the numbers in there, you have 1 times 0.5. Sigma 1 is 0.1 squared. B2 of x is 0. B2 of y is 0.7. Sigma 2 is 0.2. I need to square that guy. So since we're multiplying by 0, this thing goes away. What do you get?
0.005.
0.005? Yeah. Yeah? What about part D? Betas of the portfolio. So you need to calculate beta 1 of the portfolio and beta 2 of the portfolio. Each asset is described by two sets of sensitivities. So your beta 1 of P is going to be the weight of X, beta 1 of X, plus weight of Y, beta 1 of Y. Beta 2 of the portfolio is weight of X, beta 2 of X, plus again, the weight of y, beta 2 of y. So you're using the same risk factor, you're doing the weighted average of all of those. So the weight of x is 0.4. Beta 1 of x is 1. What is the weight of y? 0.6, right? The sum of the weights is 1. And what is beta 1 of y? 0.5. So 0.7 overall?
Yes.
What about the beta 2? You have 0.4 times 0. And then 0.6 times 0.7. So this is 0 and this is 0.42. Is that right? Yep. Questions? You good? Let me add one more question, because it's going to lead to what we're going to do later on. How much should I invest in X and Y so that my portfolio will have a beta 2 of 0.6. And then the follow-up question is, what is the beta 1 of this portfolio? So this is going to point out a couple of things. Remember, as an investor, you have full control over the betas, right? And you could possibly use that full control over the betas with a purpose in mind. And in this case, for whatever reason, we want to create a portfolio that has a beta 2 of 0.6 by mixing those two assets. The problem is that once you pick the weights, you're also going to affect all the other betas that describe the risk of this portfolio. So let's see how that works out. So let's start with beta 2 of P is equal to the weight of X times beta 2 of plus 1 minus the weight of X beta 2 of Y. Bless you.
Right.
You agree with that? What did I get 1 minus WX?
That is the weight.
That's the weight of y.
You're mixing those two things, the weight of X and the weight of Y add up to 1, so I'm writing it like that. So, out of those, all those numbers are known except the weights. So this is 0.6. Weight of X. What is the beta 2 of X? 2 of X is 0. Plus 1 minus the weight of X. Beta 2 of Y is 0.7. So now it's just a matter of doing a bit of algebra and we should be able to figure out what the answer is. So for X, for WX, so you get 0.6 equals, distribute these across, 0.7 minus 0.6 weight of X. So weight of X is equal to subtract 0.7 from both sides, you get minus 0.1, then divided by minus 0.6. And what's it, 1/6?
Would it be 0.7 minus 0.7 WX? Or would it be 0.7?
And it's exactly right,
0.7.
0.7. Yeah, distribute that, right, then divide by that, so it's 1/7, sorry. Yeah. So the weight of X is 1/7, what about the weight of Y?
6/7.
Whatever these numbers are. Yep. So what happened to the B1? This B1 of the portfolio is now the weight of X, beta 1 of X plus the weight of Y, B2 of Y. Weight of X is 1/7. B1 of X is 1. And then you have 6/7. Beta 2 of Y. No, sorry, beta 1 of Y is 0.5. So you get
0.57.
3/4/7. It should be 0.357. Is that right?
I got 0.57.
0.57. Yeah, it should be more than that. 0.57. Yeah. So, ultimately, what we're gonna do with this thing is, before going there, do you have any questions about this? What makes it difficult is the subscripts. So make sure you track down the subscripts, okay? Think of those as unique, those guys right here as unique characteristics that identify something. In a way, you can think of it as your first name and last name. Each asset has its own set of first name, last name, social security number, and all these data points, yeah? Those data points are unrelated with each other. Your first name is probably unrelated to your last name. Both things are related to your social security number. And so think of those as unique identifiers. But each of us might have a liking for a first name, a liking for a second name, so you're sensitive to those things, and a liking for social security number. I don't know why you would like that or not. Think of them that way. All those items are totally unrelated with one another. That's where they're supposed to be. But for some reason, we really care about them because we're sensitive to their values. If you want to create a portfolio, but also the portfolio, think of the portfolio as the child of two assets. The portfolio will also have a first name, a last name, and a social security number. So how do you get the first name? Well, it's the average of the names somehow. How do you get the last name? It's the average of the last names. How do you get the social security number if it was B3? What is the average of the social security number? So for every asset, you will have to repeat this calculation for each of the characteristics that identify it. Ultimately, if you think about this thing, and we get creative, what would happen if one of the two assets is shorted?
You have a negative one.
Well, you would have a negative weight. Do you agree with that? So think about what you could possibly do if you could simultaneously short something and then use the money, the proceeds from that short, to invest. So we know that every time you short, you have to use margin accounts. So what I just described is not really practical in real life, but let's suppose that theoretically you could do those things. You borrow money and you invest. What is your net weight in that case?
Over 1,000.
Let's see, suppose I borrow, I short this guy, all of it, then the weight of this guy will be a negative number, and I use then money to invest in this one. So whatever this negative weight is completely offset by the positive weight of the other. You agree with that? The technique this technique I'm describing is called arbitrage. Is where you commit no money and you use it to kind of gain a return without being exposed to risk. We're gonna use this knowledge to figure out a technique to see if we can have arbitrage opportunities in the market. The model that relies on all this stuff and the concept of arbitrage is called APT. So it's a much more powerful model than the CAPM. In fact, it allows for multiple risks to take place, multiple sources of risk, whereas CAPM only focuses on one, is the market risk. So one of the things that we could possibly do here is you could short one asset and invest in the other in a specific way, and then invest in the risk-free asset if there is a discrepancy between the two, and possibly eliminate exposure to one of the risk factors. So think about me shorting these, buying these, and then buying some a risk-free asset. The risk-free asset will have what values for the B1s, B2s, B3s. The risk-free means zero. Let's see if that makes sense. The risk-free asset, we know this number is zero for the risk-free asset. So this can either be zero or positive. This can be either zero, the betas can be any number, but we know that those values are either zero or positive. If it's zero, then it should not be in the list of risk factors. So those numbers can only be positive if they're included. So the only way for this thing to work, to give you sum of zero, is only if the betas for the risk-free asset are zero. So the risk-free asset in this model will have B1, B2, B3, and so forth, all equal to zero. So by using this long and short combination, we can choose suitable weights by using a technique similar to that, so that we eliminate one of the sources of risk. Now, if you're clever, you pick the weights so that perhaps you can eliminate all sources of risk, and you create a portfolio basically that has zero risk exposure, but some positive returns. So now you created yourself an opportunity to get free money with zero risk. So the challenge is, how do you find the weights? It's not easy. So we're gonna do that on Monday. Questions, Monday or Wednesday? Yep. So can you handle this stuff in the quiz? Start like yesterday. The single index models are easy, but if you don't see them for a while and you try to catch up at the end, that is a guaranteed disaster. So start working on this stuff now. Keep in mind that this is the best you're gonna be at this topic. An hour from now is gonna be a little bit worse. Next week is definitely gonna be worse. After Thanksgiving, all the stuff is gonna be gone unless you do it now. So don't get behind. All right.